I'm Hadas Kress-Gazit. I'm the Jeffrey S. M. Hedrick Professor, Senior Professor at Cornell in Mechanical and Aerospace Engineering. I do work on formalisms for robotics. I'm going to talk about temporal logics today, and I'm happy to chat afterwards. Okay, so what's the deal with temporal logic? So that's kind of what I want to talk about a little bit. So I have a few screenshots from the workshop webpage to kind of give you a feel of where I'm going from in the context of this workshop. So this is the discussion topics. The things I really want to talk about are how do I define tasks? So task objectives, environment definitions, all these things. Advantages and drawbacks. So I think it will be, sorry for the snark, but it'll be a little bit maybe refreshing to hear things that actually don't work. So why would you want to use it? Why would you not want to use it? And then I want to talk about what are the things you can do with temporal logic. So actually the topic is the right topic, but all the questions I'm not going to actually answer. So everything I'm not highlighting, I'm actually not going to talk about. Okay, so I'm going to talk about temporal logic. And I'm going to define, I know some of you in the audience may have seen this before. I'm assuming you didn't. I'm going to give you a high-level view of what that means. But before then, just to make the point of these are not useless. These are a few of the systems we've used in the past in my lab, and there are other labs that have used the temporal logic to do high-level robot behaviors. So from the top left, which is modular robots, together with Mark Campbell and Mark Yim at Penn. The bottom left, which is was a project with Tom Howard at University of Rochester. Bottom right, swarm behaviors. So you can see we can capture like different types of behaviors. The top right is actually not a video. I didn't post the video, it's still under review, we're still playing around with that. That's kind of a multi-agent or multi-robot situation with different types of robots. The other thing which I will highlight in a little bit is using temporal logic, you can actually provide feedback during the execution about things that might go wrong, and maybe even adjust or fix or repair the task as you're going. So these are a few examples of giving feedback during execution and repairing automatically. The ones on the left are feedback. This is the thing that could go wrong. The ones on the right are, okay, something went wrong, I'm going to fix it by blah, blah, blah. I'm happy to talk about any of these anytime. All right, so really, I don't want to spend time on, I mean, I need to show you cool robot videos because we have cool robot videos. So I'm going to show cool robot videos, but really what I want to talk about are temporal logics and what I can do with them. So this is also from the website for this workshop, and one of the paragraphs in the middle says, to facilitate feed discussion, we break instances of task specification into two complementary groups, formalisms and modalities. So I'm actually going to not accept that definition. I still think there's these two groups makes a lot of sense to me. But what I would call them was formalisms and abstractions or grounding. Those are the words I would use. So we have the how do I write it? And then I have the what does it mean? So those are the things that I'm going to talk about. And if I talk about this in the context of logic, really formalisms goes into syntax. What is the syntax of the task that I can capture? And the abstraction grounding plus the logic structure itself is the semantics. What does it mean? What does it mean in the real world in this case? So I'm going to go with syntax and semantics. All right, so let's talk about specifications. I'm going to show you a little bit of logic. If you've ever seen me give a talk, you've seen one of these slides, so I'm sorry. But what I want to talk about, I want to talk about two types of logics that we use. There are two types of temporal logics that we use. There are many different types. People use some other things, but I think these two have properties that are very interesting for robotics specifically. So I'm going to highlight that. The first one is linear temporal logic. So whenever I talk about a logic, I need to tell you the syntax. What is a valid formula in that logic? What are the symbols I can put together? And then what is the semantics? What does a formula mean? So in the case of LTL, linear temporal logic, LTL, really, it's a logic over discrete things. I have propositions. I have these pies on the top left, and these pies have meaning. But if I was to think about it in the context of robotics, I can discretize the state space of the robot, of the environment. Like you could create these symbols that represent what the robot is doing, the environment, goals, blah, blah, blah. And once I have those propositions, when I have that abstraction, now I can start composing interesting things, right? So my 30-second description of what temporal logic is as opposed to Boolean logic, where you have and or not. So you still have propositions. You can combine them using these Boolean operators. So Hadas in Delft is a proposition. It's true today. So the formula Hadas in Delft and Dylan in Delft is true today. But if I think about the world not as a fixed, propositions are either true or false, but all propositions can change with time. Now we can start thinking about temporal aspects. So, for example, always Hadas in Delft and Dylan in Delft. I wish, but no, that formula is false. But if I say eventually Hadas in Delft and Dylan in Delft, that is true because it's true right now. So I can think about these operators. So I have the notion of next. Next is a little bit tricky in robotics, so we can have a conversation about that separately. The box corresponds to always, the diamond corresponds to eventually, and the U corresponds to until. So something has to happen until something else happens. The semantics are defined over infinite traces. So I have infinite assignments to the truth values of the propositions. So for example, that's in Delft. Currently true, will be true in the next hour, will be true in the next hour. Tomorrow morning, whatever, 6 a.m., it's going to be false. Why? Because I need to go home. Okay, so the truth value of the proposition, and then I can start, given an infinite trace of the truth value for the propositions, then I can determine whether formulas are true or false. So a question of, given a formula, I can tell you whether it's true or false, given that they have an infinite trace. But I want to kind of plant the seed that also if I have a formula, I can find a satisfying trace to be able to satisfy that formula. And that's kind of where it becomes useful for robotics. Well, I think it's useful in both ways. But here the idea is you have to have a discrete abstraction. Now, the more fine-grained the abstraction, the more kind of closer it is to the real world, the less you can compute. It's going to become larger. And vice versa. The more coarse it is, the more I can compute, the more I have to put the weight on the abstraction. Does it actually, is this symbol something I can actually guarantee? So if I want to go from symbol A to symbol A being true to symbol B being true, I need some continuous controller that will do that. And the more coarse it is, the more weight I put on or the more challenge I put on the lower level in the abstraction. So just to give you one example, if I imagine I have 9 propositions. Oh, I cut off the thing. Sorry. So I have x's on the x's on the x-axis. Imagine I have y's on the y-axis, and now each region is represented using 2 propositions that are true. So the bottom left is going to be x0, y0. So x0 true, y0 true, everything else false, and so on. So what I can write is starting from x0, y0. So starting from the bottom left corner. Always, and, so they have an and, always not x2, y0, so that the region with the red kind of do not enter thing, I never want to go there. And always, well, we'll skip that one, it's a little bit in the details of the specific synthesis algorithm we're using, but always eventually x2, y2, so the top right, and always eventually x0, y0. So this task says I want to infinitely often go between the top right, and the bottom left, and I never want to go to the bottom right. So this will give you a feel for the specification, right? That's kind of this is LTL. All right, so LTL has a bunch of good properties in the sense that I can actually synthesize controllers, or I can synthesize state machines that if I execute them, satisfy my task. But the fundamental thing here is I need an abstraction. I need something discrete. And there's no timing, right? There's no explicit time. It's just steps. I'm going to do this, then this, then this, then this. A different logic we've been looking at, and not just us for sure, a whole bunch of groups, is signal temporal logic. Here, instead of, mouse. Yeah, there we go. Okay, I want to use my mouse to also people on Zoom. So here, instead of instead of now having a discrete abstraction, now really what I'm doing, I'm writing specifications over continuous signals. So this is continuous, in general, could be continuous time, continuous value signals. Really, in practice, it's continuous value discrete time signals. So basically, a signal that can have any value, but this mu predicate is a predicate over that signal. So now I can write, for example, a predicate could be, I'll show you an example. A predicate could be my distance from the table. So I'm moving continuously, so that number changes. But I can say that the predicate is true if the distance between me and the table is less than 1 meter, and the predicate is false if I'm further away. So you need to have this predicate function. You can see that's here in the H. So given a continuous signal and given a predicate function, those are now my building blocks that I'm writing over. The other thing about STL is that it allows me to add timing. So I can put timing intervals, here. So again, I can say always within time A and time B, this has to happen. Eventually between time A and time B, this has to happen. So I can write formulas in STL, and I can evaluate whether they're true or false. The other thing that is actually really awesome about STL is that it also has a quantitative semantics. I can tell you how far away I am from satisfying a specification. For example, if my specification is always Hadas more than 1 meter from the table, then if I don't fall, if I'm here, I can say my robustness is 0.5. Because it's 0.5 until I'm up to kind of almost violating. On the other hand, if I'm very close to the table, my robustness right now is minus 0.9 because I'm literally right next to the table. So the sign of the robustness metric tells you whether it's true or false, but you also have a number that tells you how far you are. So you can think about robustness, which is really nice. Okay, and this would be an example. I think I'm running a little bit late, so let me not go through this example. But this is an example of kind of picking up an object, drop it picking an object, drop it in one of the boxes that we did. And there's a bunch of kind of things here. All right, questions I get often. Not so much. I wanted to mention PDDL, so the planning domain description language. I keep forgetting what the P is. And it's not PDDL star, but I'm putting a star because I'm going to really generalize here. There are many variants of PDDL. There are things that can do different things. I'm overly generalizing. But really, the way you want to think about this is the basic building blocks in temporal logic are states of the world. The basic building blocks in PDDL are actions, things that change the state of the world from a precondition to a postcondition. Typically, we have, and PDDL allows you to parameterize those, which is really nice. We have formulas, so typically, or let me go with planning. Planning started from the fact that you want to reach a goal state. And for temporal logic, really, you care about the trajectory. So if it's just you want to get to a goal state, temporal logic might not. Anyway, there are trade-offs. It's always trade-offs. Temporal logic is good to put constraints. So for example, negations. I don't want something to happen. That's a little more challenging to do in the PDDL kind of planning world. And very often what you would get, again, I'm overgeneralizing because there is contingency planning. There's a bunch of stuff in the planning world, but like the basic original PDDL is you get one plan. While when you synthesize temporal logic, when you synthesize LTL, you typically get multiple plans. You can kind of choose from a bunch of different plans. All right, so I'm going to do just a quick plug for a journal that I used to be on the editorial board of. I really, really like. It's Annual Reviews of Controlled Robotics and Autonomous Systems. And there are a bunch of papers, both on the planning side and on the kind of temporal logic side. One of them is mine, so, which I talk about synthesis in this context. So I highly recommend that. The journal in general is really fabulous. So take a look at that. Okay, so hopefully you get a little, for people who've never seen this before, I hope you kind of get a little bit of a feel of what LTL and STL are. And really what I want to do is I want to just give you snippets of what are the things we can do with this. So first thing that's kind of, well, not first, verification. Verification is the process of, given a system, someone already built a system, given a requirement, can I prove, or can I find a counterexample that the system satisfies the requirement? That's verification. I already have the system, I'm checking it. I want to verify it. And there are many, many techniques to do this, and there are probabilistic techniques and so on. But you have to have a requirement. And the requirement is given in temporal logic, typically. So this is, I wanted to kind of, I'll show you snippets of things we can do with this. So this is kind of fairly recent work where we look at a black box controller, and we're able to do this probabilistic verification of a task we're able to do probabilistic verification by both providing the probability of success or the probability of failure of the task and examples of failures. So kind of we can sample from some distribution to show you what the failure modes are. And in this case, we kind of see two different failure modes. I'm not going to go into the details of what this is, but obviously, just to give you a little bit of a taste. So synthesis is the dual problem. Synthesis is I have a temporal logic formula. Let me generate a system that's provably correct by construction, that will do what I want it to do. Or tell me you can't. That's a process of synthesis. That's the annual review paper I was talking about that for LTL. The interesting thing that what we've been interested in lately is also is synthesis, a priori synthesis, and then also synthesis on the fly to repair if something changed. Just to give you a little bit of a feel, the task was pick up an object, put it in the box, and here what we did is we modified the task as it's executing, added basically and avoid obstacles. So it's just a conjunction. You just added a few more symbols to create a totally different behavior. This was the and avoid cones. On the right side, he's going to just introduce another box. So literally, he just wrote a few more symbols in a text file, uploaded it, and then changed the task immediately. And now it's reacting also to where that box is. So we can do this conjunction, we can do disjunction, we can kind of change things on the fly, which we can do because we have this formalism that captures what we want to do. We can provide feedback. We can explain ahead of time why we might not be able to satisfy the task. We can explain as we're going, for the STL case, what is a possible failure mode, what we call this pre-failure warnings. What might happen now that will make me fail? So we showed kind of, here you'll see, actually let me skip this. So really what's going on here, I'll skip this. Now with the whole with learning these days, right? So there's a lot of things going on. She's laughing at me. Is there space for these kind of formalism? Why not just learn everything end to end, And that I am willing to have a really long conversation about that and my thoughts there. I do have thoughts. But there are some really interesting connections between temporal logic and learning, and especially since it's such a concise and precise way of writing a specification, of explaining what we want to do. So there's a bunch of work. I mean, this is just a random Google. I need to go more deep into what people are doing. It's really cool. In terms of using temporal logic as reward functions, learning them from people, using them to ensure safety of RL. There's a bunch of kind of going back and forth between There's some going back and forth between temporal logic and a reward function. And then the final thing that I am, we just submitted a paper on evaluation. That is a big pet peeve of mine right now with reading a lot of papers, the evaluation, especially the kind of the large models. If you write papers on large models and you don't evaluate them, and if you don't spend the same time you use to train it to evaluate it, I have thoughts, okay? So here's this was actually rejected from RSS, and the reviews, they had good points. Resubmitted, I'm gonna probably post it on archive probably tomorrow. But here, what we're looking at right now is we're looking at each line corresponds to a different policy. It doesn't matter what the height, it's just a difference in height because we can see it better. We rolled out a policy using different models. The gray line is 0, It's an STL specification, and everything on the right of it, all the positive numbers, are the specification is satisfied. Everything on the left side, specification is falsified. So the task, the rollout violated this task specification. So you can see the orange policy, and I don't care what the policies are, because that was not the point. The orange policy doesn't do quite as well as the blue policy, for example. So the second from the bottom versus the bottom one. The bottom one is never on the left. The orange one is on the left. So I think this is a nice way, and this is, I should also mention, this is all physical robots. This is not simulation. It is much easier to do this in simulation because you have ground truth, because you have basically, you have full information in the simulation, right? So we're thinking about implementing this as well. But even for physical robots, we can do this. So I think that was something that I'm going to start pushing, because I think it's cool. I think it's cool, but we'll see. We'll see what the community thinks about it. Okay, to summarize, and I don't know if I'm good on time. Look at that. Even with the technical stuff, just talk fast. So summary. Temporal logics are expressive. They can capture a lot of things we care about. We care about goals, things that the robot eventually can do. We care about constraints, things that the robot should not do, right? I don't want you to run into the wall. Now, do I want to specify that in temporal logic? No. But if I have a specification that is follow a person, but if there's an alarm, I want you to follow them. I want to follow in front of them. But if there's no alarm, I want you to follow them in the back. Or if there's an alarm, I want you to lead them. If there's no alarm, I want you to follow them. That's a longer collision avoidance, and that is super easy to specify in STL. We have actually another projected paper from Aerospace with kind of a user study that we did with STL. So there's a lot of things we can express. They are useful for different settings, for different problems that we might want to have. So verification, synthesis, I think they have a place in learning and evaluation and all that. But nothing is perfect, right? Nothing is perfect. Nothing is a silver. There are no silver bullets, okay? So what are the drawbacks of temporal logic? So for LTL, abstraction. Like I said in the beginning, the more fine-grained the abstraction, the easier it is to match to the ground in the real world, the more we're going to run into the second issue of scalability. So there's this trade-off of abstraction scalability, because if I could abstract the world into 0.1 centimeter voxels, the whole world, and write a specification on that, awesome. I can definitely do that. The connection between the symbolic and the physical is really easy. There's no way I'm computing that ever. Okay, so there's a trade-off of abstraction and scalability. And then, why did I write preferences? Now I don't remember why I wrote preferences. So I think, I know I wrote that. So currently in using LTL and STL and using these temporal logics, it's not so much the formalism, but if you want to have, it's more kind of the algorithms that you use, so verification and synthesis. If you want to have like hard constraints, soft constraints, if you want something that are just like optimization, STL a little bit better, because STL you solve as an optimization problem, so you can put an objective that's more interesting, or not, that has to do with preferences. You can also always have like another input that says, if this is true, then ignore that. So there are ways around it, but it's not the most natural in terms of capturing soft and hard constraints. But I think that's my spiel. Thank you so much.
In the interest of time, can we have just one question from the audience? Yes.
You mentioned that you are highlighting these two temporal logics specifically because they are nicer for robotics. Can you elaborate on what makes temporal logics nice or not so nice?
Okay, so the question was, I'm just going to repeat for Zoom people. The question was, I mentioned that LTL and STL are nice for robotics. What about other logics? Are they not as nice for robotics? It's not that they're not as nice, but LTL and STL also have trade-offs. So LTL I can synthesize ahead of time, and I know ahead of time whether I can perform the task or not if the abstraction is accurate. STL typically is done like it's an optimization problem that's done on the fly, so it's hard for me to give there are some ways to give guarantees over a finite horizon. You can provide a little bit less guarantees a priori, but they capture different aspects of robotics in the sense of STL is better for kind of leaning into the continuous versus LTL gives you a little more guarantees. Other logics have time, so there's like logics that have discrete abstraction, but they have time. I can still use that, but it doesn't quite, it's not farther enough from LTL that I would want to use that, right? There are other logics, I think these two captures like, it's not that the other ones are not good, but these ones have been used and we have algorithms to actually synthesize robot controllers from this, and it's kind of a little bit better understood. You can think about the thing that they don't have parametrization. But then you go into logic that are much harder to deal with because you start going to first order logics, which is, synthesis there is intractable. So there's a trade-off here, and those two kind of capture different subsets of the world that would be useful. Not necessarily that others are bad, but these are kind of capturing good subsets, I think. Yeah. Another question? Can I take it? I take one more question?
Okay, sure.
Go ahead. Yeah.
I'm at the verge of robotics and also the software community, and there in formal methods, there is some work to try to create patterns applied to robotic missions concretely using the linear temporal logic. And so I was wondering in regarding to this parameterization, or because this can become arbitrarily complex depending on so if the mission is really complex and with the level of abstraction, it can be arbitrarily complex. So they try to create this collection of patterns that represent most general robotic missions. Do you see any connection value in generating as a community such a collection of patterns to accelerate the work on validation using methods like the temporal logic, for example, so that we share the patterns in which we describe our constraints, for example, instead of using, but you can describe it in different ways, depending on what the task, what your opinion.
So the question is it, I'm going to rephrase a little bit and let me know if I misunderstood you. The question was about patterns. Can I generate a priori formulas that represent different aspects of robotics and then I just mix and match? I don't know so I don't know enough about this. I think if it helps with scalability, meaning the pattern itself, I don't see that as quite as useful. If there are methods for me to pick and choose different patterns and just automatically generate the automata that satisfies those in a way that's much more computationally efficient, yes, absolutely. I think that would be awesome. Yeah. So it's more the synthesis part, the getting the specific, getting getting the system, the scalability there, not so much the writing the specification itself. Yeah. Okay, now I'm done. Thank you everyone for that.